Welcome, everybody. This is the beginning of chapter 4 of Haskell, the Graham Hutton's textbook. And in this chapter, we are going to learn how to define our own functions. And the idea is to build on the prelude functions which are already available with us and build new functions out of those, and also build newer functions out of the new functions we built out of the prelude functions which we have to begin with, okay, and so on. So the idea is to keep building new functions based on old functions and come up with solutions to problems. All right. So that's the emphasis here. And in this chapter, the emphasis is a little bit more on the syntax and the different patterns and different ways of writing such functions rather than actually solving problems. The solving problems comes in the subsequent chapters 5, 6, 7, and 8. Okay. All right. So let's get started. The first mini topic here is new from old, and basically exactly what I just mentioned. So we already looked at some prelude functions in the previous chapters, right? And we're going to use some of those and build newer functions, and maybe some of these new functions which are defining are probably already in the prelude, but at least at least the first one, I believe, even is in the prelude. I guess a simple way to test that is to create a new cell here. Let's see, and just say even 4 and run this. Yep, true. So even actually happens to be in the prelude, but let's say that it was not. Okay, and we know the mod function, uh, which basically gets you the remainder after dividing by an integral. That is a built-in operation. So we're going to use the mod to build the even. Okay, so we are pretending even is not in the prelude, and we are writing the definition. Okay. Even signature would be even double colon separates the name of the function from its type, or name of the expression from its type, and in this case the expression is just a function. Okay, and the type here is a arrow bool. So this is the type, a arrow bool. A is a type variable and bool is a boolean. Arrow separates the input from the output, okay, for this function. And this here equal greater sign separates what is called the type constraint from the type signature. Okay, so in this case the type constraint is a is an integral. Okay, integral class, type class. A belongs to the integral type class, and we discussed the type classes last chapter. The integral type class requires types to implement the div and the mod functions. Okay, and obviously we need the mod function, and that's why we say integral a here. Okay, so that the first line is important. It's the type declaration for even, and the second line is the actual implementation of the function even given a parameter n or argument n equals, and this expression here which says that n mod 2 equals 0. So if n mod 2 n divided by 2 gives you a remainder of 0, then it's even, otherwise odd. As simple as that. Okay, so this illustrates, assuming even was not in the prelude, the development of a function called even based on, if you look at rest of the stuff here, we are using in the implementation one of the built-in functions called mod. Okay, and also another built-in function called equal, and so on. Okay, so these are using those, we built a new function, and when you test this out on even 4 and 5, you get the correct answers. Okay, now let's look at another function called split at, and again probably this is not in the prelude, but let's just verify that. Split at position 3, list 1, 2, 3, 4, 5, 6. So that's a list 1, 2, 3, 4, 5, 6, and a position is given. Yep, split add is also built-in. Oops, I thought we are building new functions out of old functions, but apparently we are not. Okay, but the idea is that if split add was not a built-in function in the prelude, then this is how we would build it. Okay, So let's see what is happening here. Split at, what it does is that it takes an index. Oh, let's look at the signature. Okay, its signature is a little bit longer than the previous one. It says int arrow bracket a arrow parenthesis and then a couple of bracket a's there. Okay, so it's a function, and it because there are two arrows, we can safely say that it takes two inputs. Okay, the number of arrows equals number of inputs. Okay, in this case, all but the last item in that sequence of types which are there before and after the arrows, each one of those, and there will be three of them here, right? Because there are two arrows, there will be three types which are sitting before and after those guys. So all but the last one would be the inputs, and the last one would be the output. Okay, that's how you should read these signatures. Only thing is that we read these inputs, or when you provide these inputs at runtime to the split at function, you can provide them one at a time. You can also stop without providing all of them. Okay, so those are called partially applied partial applications of functions. Okay, anyway, int is the first input, which is the index or the position in a list, and the second input is a list of a, and here we don't care what a is. Okay, so, you can see that there's no type constraint sitting to the left of this signature. Okay, unlike the previous one where we had integral a in the previous one. Here you see this, so there was a type constraint here, but in this case we don't have a type constraint, which means that this a could be of any type. Okay, which is fine, because while we are splitting a list at a particular position into two lists, we don't care what the items are, we just want to split them, right? Split the whole list into two lists. All right, and the definition implementation is pretty straightforward. You can see that at position n we want to split the list xs, and all we do is call the take and drop functions which we learned earlier. Okay, take n xs will get you the first n items in the list xs, and you'll get a list, and the drop n xs would get a list by dropping the first n elements and keeping the remaining ones. Okay, so by doing these two operations, we actually can split the list into two parts. Okay, at position n, exactly at position n. Okay, and here's an illustration of that. Okay, and the third one is a pretty trivial one. I think we saw a recip function or operation which was built in the fractional part, and I also commented that it's really useless because we can always do 1 over n instead of saying reciprocal of n. Okay, 1 over n seems to be more compact notation than recip n. But anyway, suppose you wanted to build the recip n, but it's also a built-in function. Okay, because any class, type class which implements the fractional method, and there are two, divide, slash, and recip. Those are the two methods or functions. It's already built in, so I wonder why we are writing it. But anyway, recip n equals 1 over n is how you'd write it. Okay, or how it would be written in the prelude if I want to justify this. Actually, all three examples, I thought we're going to write new ones from old ones, but the old ones were actually, the new ones were actually old ones. Okay. Anyway, jokes apart, this actually illustrates how you build new functions out of old functions. Okay. All right. But that will be the general philosophy in all of Haskell. Okay. I have mentioned many times that writing programs in Haskell is like building a circuit, where you take built-in components, chips, or whatever you want to call them, and combine them in a certain way, and you get a new chip, which has a different functionality. Okay. All right. So now we are going to learn some of the syntax of which is very some of the syntax which is very useful. In particular, the conditional. If you're programmed anytime in any language, the conditional expression is very crucial in programming, right? The if then else. Without that, very difficult to solve many problems. And we have conditional expressions in Haskell. We don't have conditional statements. We don't have a single statement. Okay, there's no thing called a statement in Haskell. Okay, there are only expressions. Everything is an expression. Okay, including the functions. They're all expressions. Okay, they're all actually lambda expressions, if you remember your lambda calculus. Okay. Anyway, coming back to conditional expressions, those are very useful in composing functions. So here is the syntax. We're going to look at a couple of examples, okay, and we'll go through some of the built-in functions like absolute value of a number, right? Absolute colon int arrow int takes an integer as input, provides an integer as output, and obviously if it's a negative number in input, it returns a positive value of that. Okay, absolute n. This is the implementation, the second line. Absolute n equals. Now, obviously, we need to use a conditional, right? Because if the input is negative or positive in this case, if n is greater or equal to 0, then the answer is n. Else, the answer is minus n because it's negative. So a negative of a negative will be positive. Okay. So this is how you'd write it. Notice that if, then, and else, all three keywords must be present in this expression. Okay. No exception here. Okay. There's no elif and it's all if then else. Okay, and because of the strict requirement that the else is always required and the then keyword is also required, there is no cause for ambiguity in nesting. Okay, the ambiguity comes in other languages because other languages allow both the if then and the if then else statements. And when you start nesting one version inside another version, ambiguity comes up. Okay, but there's no ambiguity in the if then else's in Haskell. Okay, so that's how you would write absolute. And here's two runs. Okay, let's go to the cell and run it so you can see the 4 and the 4. Okay, all right. They can be nested, so as we just remarked, and an example of that will be the sign num, okay, or signum, okay, signum. Remember, this is also a built-in function for numeric class, I believe. Yeah, numeric class, correct? Or is the or no? It's a numeric. Okay, it's a numeric class, a sign num. Okay. What it does is that given a numeric value, it returns the sign of the value, whether it's a -1 or a 0 or a +1. Okay, if the value is 0, then answer is 0, sign num is 0. If the value is negative, then it's -1, and if the value is positive, the value is 1. Okay, so this is sign num. Okay, all right. This is how you build it. Now this requires a nested if then else, right? Because there are three cases here. So you can see that sign num n equals if n less than 0, then -1 is the answer. Else, if n equals 0, then the answer is 0. Else, the answer should be 1. Okay, so because there are three cases, we write it this way. Okay, if then else nested. Okay, all right. You can ignore this. Yeah, this guy here. Okay, this part here, because this part is just my Jupyter Lab warning. It is basically saying that, hey, you're a silly guy. You cannot write slick code here. Okay, if the nesting is terrible, why not use guards? It says. Okay, but this is fine. This is correct, and actually you do see the answer -1 and 1. Okay, we're going to learn guards in a minute, and soon you will stop using if then else yourself. Okay, and we'll get rid of this warning as well. Okay, all right. So nested in Haskell. Conditional expressions must always have an else branch, which avoids any possible ambiguity. We already mentioned that. Okay. Okay. Now let's talk about the guards, which this Jupyter Lab was warning me about. Not warning, but suggesting. It says, "Oh, I found this. Why not use this?" Okay. This looks much better. This looks terrible. Okay. All right. Guarded equations. These are called guarded equations. Okay. So these are things you write in the body, right? In the body of a function, like here. We write one or more equations, okay, which defines the function. And typically you want to write the equations in such a way that it covers all possibilities for the inputs, okay, because you want to define this function completely, right, fully. So if you leave out certain inputs in your equations, then your function is not specified fully. And when that input which you left out comes in as parameter or argument to the function will fail because it will not have, it won't have an answer for that, right? So that's why you had to get used to trying to cover all bases or all cases, basis cases, yeah, that's good, in writing these equations in the body of the function, okay? So guarded equations are a nice way to write cases, different cases, and it looks quite uniform. Okay, it's a little bit you probably this is a feature which is not available in other languages very much. Okay, maybe it is, but certainly in Java and Python we don't see this. So but let's look at what it is. Okay, as an alternative to conditionals. Okay, so basically guarded equations are absolutely not necessary. You can always write the if then else and nest them any way you want and still solve the problem. Okay, but the guarded equations, you might have seen this in math. Okay, in math you have a very big curly brace. For example, when you say that f of x equals, and there are two cases or three cases, let's say x greater than 0 something, x equals 0 something, and x less than 0 something, or sometimes you say otherwise, right? And then you put a big left curly brace, and then you write three lines next to this. Okay, exactly same. So this guarded equation is the same. So you can see that a lot of math ideas, mathematic ideas from mathematics are brought in, and actually that is natural because Haskell is a mathematical language of functions, right? Okay, so this is how you write those equations. Okay, so you write the expression whose value, or basically in this case it's the function, right? Abs n, absolute. I'm going back to the absolute and the signum. Okay, absolute value of n. This is the body of the function. Okay, abs n is the body of the function, and typically we'll say equals, and then we'll write an if then else there. Okay, but instead of that, we can actually put guards. So these are called guards, the bar signs. Okay, so after this you can put any number of bars. Okay, and write a condition and then equal to, and write the actual return value, okay, which is for that condition. Okay, so you can see that previously we said that if n is greater than or equal to 0, the answer is n, else it is minus n, right? So so we write the first condition, n greater than or equal to 0 here, and then say, oh, if this is true, so there's no if here. Okay, it's just the guard. The guard is automatically conveying the fact that there is an if there, if this condition. So what you write after the guard must be a condition, okay, a boolean, true false. Okay, n greater than or equal to 0, and then you'll say equals, if this condition is true, then the answer for absolute n. So it's sort of turned around. So this whole line can be read as follows. Okay, if n greater or equal to 0, then absolute n equals n. Okay, that's how you read it. So it's sort of twisted, but it's once you get used to it, this is a very nice way to write it because it resembles the mathematics, the braces in the math. Okay, the big brace, not the regular brace, but the big gigantic brace you put. Left brace, you say f of x equals, and then you throw in a big left brace, and then next to the left brace, which is occupying a lot of white space, to the right of it you can write multiple lines, and in each of those lines you'll write the actual answer for the f of x, and then you'll probably say comma, and then write a condition, say x greater than 0, x less than 0. Okay, so here we write the condition first and then we write the value. Okay, all right, so now there's a special condition called otherwise, okay, which obviously is the else equivalent of the else. Okay, so otherwise equals minus n. Okay, so typically these kind of guarded equations end with the otherwise. Okay, that's all. So this is how you write. Now this looks a little bit cleaner or beautiful, more beautiful than this guy here. This if then else here. Okay. I mean, this is short, so I think both look okay to me. But in the next case, where we do sin num, where there was a nested if then else, this looks much cleaner. Okay, sin num of n is minus 1 if n less than 0, is 0 if n equals 0, and equals 1 if otherwise. Okay, so that's how you write it here. So you can string together all the conditions one below the other after the guards. Now you must repeat the guards here. Okay. So the guard, all these guards are separating the actual function call, okay, from the return answers. Okay, all right. The catch-all condition, which is the otherwise, if you actually look at prelude and the definition of otherwise, you'll see that it is true. Okay, otherwise is another name for true. Okay, interesting. And the reason it's true here, otherwise is true, is because typically not typically, it's always the case that these conditions are evaluated, or these guarded equations are evaluated from top down. Okay, the first guard will be checked, and if that is satisfied, then or true, then -1 will be the answer, and none of the others will be skipped. Okay, and then if this fails, if this condition fails, then it goes to the next one, and if that succeeds, then the answer is here, and then the next one is skipped. Okay, so the last one obviously is otherwise, and we want this condition to pass, right? The otherwise to pass when you reach there. Okay, and that's why otherwise is given a value true. So otherwise is another name for true in Haskell. Okay, so true will always be true. So that's why in the worst case, when none of the conditions succeed on the top, the one will be the answer. Okay. All right, so that's the catch-all otherwise which is available. Okay, so we learned guarded equations. We learned how to write conditional expressions first, and then guarded equations, which is a substitute for conditional equations. Okay, now you can certainly use both. Okay, some places the if then else looks cleaner, neater, or simpler maybe. Other places guarded equations look good. Okay, either way is fine. Okay. Now comes the more important aspect of writing functions, and that is called pattern matching. Okay, and the pattern matching is very useful to cover all the cases of the inputs. Remember, I said that every function must define all the cases. So typically, the function. Let's look at this example. The not. Okay, not is a function from bool to bool, right? So we have to cover all possible inputs. The good news here is that the bool has only two values, true and false, right? So there are only two cases. So you can actually write down both the cases here, not false and not true, and then write equations for those. So in some sense, this part what you write here next to the function for the input of the function, okay, is referred to as the pattern. Okay, even here this n was a pattern. Okay, this n is a pattern. Here as well, this n is a pattern. Okay, so in those cases it was pretty trivial pattern. N was n, or false is false and true is true. So you write the equation not false equals true and not true equals false. Okay. But let's take a little bit more complicated examples again in the Boolean world. Okay, the and. Okay, this is how you write the and operator, and of two things. Okay, it's not a and d, but it is ampersand, ampersand. Okay, I don't think it's a and d, but let's just verify. Okay, let's just verify. I just true and false. Yeah, got an error. So it's not that, but it has to be this one. So we came from Python world where we started in Java world, I think so, most of us, and we used this symbol and ampersand, ampersand for and then we switched over to Python world where this was not a problem. This was a problem. Okay, so we had to say a and d there in Python. I'm going to break this cell here. Okay, yeah. And then now we are back into Haskell where we are going back to the ampersand, ampersand. Okay, anyway, that's the ampersand, ampersand is the and operator. Okay, and obviously it takes two inputs, the bool and returns a bool. Okay, so this is one way you can implement the and operator. Why? Because there are two possibilities for the one input, two possibilities for the other input. So 2 times 2 is 4. So there are 4 possibilities for the inputs. And you sort of enumerate all 4 cases here, true, 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 false, false, true, false, false, and then write the truth table here. So this basically is the truth table for and, right? But you can see that because it's false in the other 3 cases and true in the first case, we can actually do a pattern match here and write only 2 equations. Okay, the first equation is true and true equals true. And then the second equation, we use what is called the underscore or the wildcard. Okay, this is a pattern match feature which allows you to match the input value, which is a bool, with the underscore. Okay, which means that it could be any value there. Okay, that's what it means. Okay, any value, and in this case, it's true. Any of the 2 values, true or false. Same thing here, because in those cases, the answer should be false. Okay, so you might be worried that any case here, so this is true. This is true, so true and true is true, is false. So you might be worried about that. Don't worry about it, because always these equations are also executed top to bottom. So if the first equation executed, that will be the answer. The second will be skipped. Okay, so very much like in the guards. Okay, so this is important to remember so that you don't get worried that the ampersand and ampersand will cover the true and true case. It will not cover the true and true case because this one ampersand, the underscore and underscore appears after the true and true. Okay. All right. Now, if you think a little bit more, I think this second definition looks okay for and, but this one looks a little better. Okay, let's see what it is. Okay, true and b equals b, false and ampersand equals false. Okay, this is quite interesting. I think if you are used to lazy evaluation, you might understand exactly what this is. Okay. If the first input to an AND is true, then the second input comes into play, correct? And whatever the value of the second input is, that's the output as well. Okay, if the second input is true, then the output is true. If the second input is false, then the output is false. Okay, so you have to evaluate the second input only if the first input is true. Okay, in the case of AND. And if the first input is false, then you don't have to calculate what the second value is. The answer is always going to be false. Okay, that's the idea behind the lazy evaluation. And you can see that this one sort of mimics the lazy evaluation, and these two equations look a little better, okay, compared to this one, because here we seem to have this one case which is common to the two, and we were worried, right, saying that, oh, but luckily Haskell helps us out and evaluates the first one first and stops and does not go to the second one. Okay, but this is a better definition. Okay, so the idea is that the patterns are matched in order. Okay, so this example would not be correct. Okay, for actually if you just turn these two around. Okay, if you put this after this or here, excuse me, yeah, actually, in this case, if you could turn them around and it'll be fine. But in this case, if you turn these around, if you put this second and this one first, and the reason is that there is a common case to the two of them, right? So then you'll always get false here. So be careful. Try to use these underscores carefully. They should appear in subsequent cases rather than in the beginning case. In the beginning case, if you put it, then the other cases will never be used. So you will probably get wrong answers there. Okay. Anyway, so that's the pattern matching. Now we have other types of patterns for lists, and I guess we're going to cover that in a minute. Yeah. So tuples and lists. Yeah. So we're going to cover the tuple patterns and list patterns here. You can see that tuple patterns and list patterns. So let's look at the tuple pattern. Tuple patterns are a little bit easier to understand. Okay, let's say that we are looking at the first and the second function, FST and SND. These, what they do is they take a tuple or pair. Pair is a special kind of tuple. Okay, tuple can have any number of items, but pair contains two items. Okay, so pair is a tuple with two items. So let's say a pair AB, okay, is the input, and then the output is A. So we are extracting the first item from the pair. Okay, so this is the pattern. You see, x comma underscore within parentheses. So that's how you match a tuple. Okay, parentheses, within parentheses you can string together a sequence of variables or underscores or whatever it is, and separate them by commas. Okay, so in this case we are saying x comma underscore within parentheses. Okay, and what this would do is it would match any tuple which has two components. And the first component we are going to name it x, and the second component we don't care what it is, and that's why we chose the underscore. Okay, underscore is the don't care, is called the don't care variable. Okay, all right. So if you had x comma underscore as the input for first, then x is the output, right? Because that's the first component x. Okay, you name the first component x, don't name the second component, and then return the first component with the same name you chose. Okay. And the second one is similar, okay, SND of underscore y equals y, okay. So this is how you use patterns for tuples, okay. Tuple is it's a useful, but not so useful for parameters. If you remember, we discussed in currying parameters, we try to avoid tuples as parameters, okay, but sometimes there are some occasions where you need it, okay. And then the list patterns, I think we have seen this before. It's the cons operator, okay. So internally, let's discuss what this is, list pattern. Internally, every non-empty list is constructed by repeated use of the cons operator, the colon, right? I think we have seen this in previous classes, previous chapters. Okay, cons. It's called the cons operator. Okay, and what the cons operator does is that it takes two inputs. Okay, it's an operator. You can use it infix, so you write something to the left of it and something to the right of it. Okay, and what you write to the left of it is a single element, and what you write to the right of it is a list of elements. Okay, so what this does is that it adds this single item into the front of the list. Okay, so this list 1, 2, 3, 4, which is a very straightforward, common, simple list of 4 integers, 1, 2, 3, 4, is actually the same as 1 colon parenthesis 2 colon parenthesis 3 colon parenthesis 4 colon the empty list. Okay, this is how you cons. You start with the empty list and you cons 4 into it. Okay, that means you add 4 to this list in the front. So 4 goes to the front of the empty list, which means it's just the list with 4. Then 3 goes in the front of the output of that, which is just a list with 4. So 3 will go in front of 4, and 2 will go in front of 3, and 1 will go in front of 2, and that's how you get the 1, 2, 3, 4. Okay, so this list 1, 2, 3, 4 on the left side, and this list here constructed using the cons operator. Remember homework 1? This is exactly that. Okay, so again, you can ignore this. It's saying that why are you writing this way? Why didn't you write that way? Is what it's suggesting. Okay, but it is true. Okay, so this equal equals is true. These two are the same things. Okay, so now let's look at some functions which take lists as inputs, and how do you do the pattern matching there. Okay, so let's say that head and tail, these again most of these are built in the prelude, but let's just see how it is built in. Okay, given a list of a, head function returns the first item in the list. Okay, or an item a in the list which happens to be the first item. So head of x colon underscore, that's how you would write a list which contains x as the first item, and colon is the cons operator, and underscore would be the list into which x was added. Now we don't care what is there after the x, because we are interested in the x, right? So x would be the answer here. X would be the head of that. Okay, and tail, if you want to find the tail of a list, tail is another function. We have seen this. So the pattern match here would be underscore colon xs. Okay, xs is the rest of the list, which is actually the tail. Okay, and in front of it we add something, but we don't care what it is, and we call it underscore. Okay, underscore colon xs would match. It's a pattern which matches a list in which we have explicitly named the tail of the list as xs. Okay, and similarly x colon underscore will match a list in which we have explicitly named the head of the list. Okay, x. And that's how these two functions will be implemented. Okay, now there's a danger with these two functions. If you provide the empty list as input, both will fail. Okay, both will fail. So here it is, head of empty list. When you run this, you get a prelude dot head. There's a problem with that, empty list. Okay, so you have to be careful with head and tail. You probably have to check if it's empty, then do something, return something else, return something else. Okay, and we may come to some of these error situations later on. Okay, now the other important point is that this x colon xs, or this colon, this one here, needs to be parenthesized. Okay, very important, but otherwise you get an error. Here's the error. Okay, so head of x colon underscore equals x. Okay, that is how you would implement the body of that function, right? But this would give an error because the application operator, okay, the function call operator, which is the space between the head and the x, okay, has the highest priority, okay, even higher than the colon operator, which is here, okay, the colon operator, which is the cons. Okay, so because the apply operator has higher precedence over colon, when you see an apply here and a colon next to it, okay, with an x in between, then head applied to x will happen first. Then the result of that will be const into the underscore. Okay, and that's incorrect, right? Because x is an element, it's not a list. How can you find a head of an element? You can find a head of a list, okay, but you cannot find a head of an element. Okay, such as a number 5, right? There's no head for 5. there's a head for list containing 5, but there's no head for 5. Okay, so there'll be a type error, and that's what we are seeing here. Okay, so if you want to do this, you have to parenthesize that, and that's exactly what we did here. You can notice that we parenthesize this part. Okay, always remember that the apply application operator, the function application operator, has the highest precedence, and that's because that's the operation which does the computation for you in this model. Okay. All right, here's something, I don't know what this is. Head of 10 colon 20 colon empty list. Yeah, so this is a list constructed differently, not the but it's the same as the 10 comma 20 list. Okay, and the head of that would be 10. Okay. All right, and the last last but one topic in this chapter. I hope we can wrap it up. Okay, I think so. Maybe another 5 minutes or so. We have seen lambda calculus before, so we can actually write lambda expressions in Haskell. Okay, it's not a surprise because Haskell is built on lambda calculus, right? So lambda expressions are essentially the same as functions, but unnamed. So functions without names are basically lambda expressions. Okay, unnamed functions. Okay, so and you can do that. So here's an example, and instead of I think the lambda expressions are available in Python as well, and in Python we had to spell out the word lambda, Lambda. Okay, the good news is that in Haskell lambda is spelled backslash. Okay, so you have to say backslash for the lambda keyword. Okay, all right, so here's a function which is inside parentheses. Okay, and then it's applied to the 10 as the input. Okay, but let's ignore the 10 for the moment, and let's look at this function which is inside the parentheses. This arrow, which is the same arrow as the arrow which we use for defining the types of functions. Okay, on the left side of that is a lambda x. Okay, and this, so if you're familiar with the lambda calculus, then this arrow is like the dot. Okay, lambda x dot x plus x. Okay, so on the left side of this is the input lambda x. Okay, and the body of this function is x plus x. Okay, so in other words, this is a unnamed function which takes one input x and returns the value x plus x. Okay, so it doubles the value. So if you take this function, write it like this, and then put the 10 next to it, okay, and run it, you get 20. And if you change this to 20 and run this, you get 40. Okay, so you can see that I'm calling a function with different values, and this function has no name, the nameless function. Okay, why are lambdas useful? There are a lot of reasons. Okay, here actually let's go back. Lambda expression can be used to give a formal meaning to functions using currying. Remember, we talked about currying in Haskell in the previous chapter, basically taking the inputs one at a time. Okay, now using lambda expressions, you can actually get a better understanding of the partial applications of functions. Okay, so let's look at the add example, because it took two inputs, int and int, and returned a sum of those two numbers. And this is how you write it: add x y equals x plus y. Okay, now you can write it differently like this as well. Okay, let's look at this. Okay, so int is the and I told you that this thing right justifies this arrow here in the type definition, type signature. Okay, so technically this int arrow int is this int arrow parenthesis int arrow int. Okay, right one first and then left one. Okay, so and that's how currying works, right? It takes only one input and returns a function which takes the other input. Okay, so now you can see that because int is the first input and the output is a function, and lambda expressions are functions, so you can see that the add is lambda x, which is the first input. Now you can see that we don't take any input here. Okay, add is the function. Okay, so that's very interesting, because now we are saying that add is this function. Okay, and what is this function? It's a lambda expression which takes one input x and returns another function, which is this guy, which takes the second input y and returns x plus y. Okay, so using lambda expressions, you can say that add equals, you don't provide the inputs here. Okay, you don't, because add is the function which corresponds to this lambda expression. Okay, so a nice way to justify the currying. Okay, I hope you understood this. Okay, it's subtle but interesting and important. Okay, Now, that is one reason. You can use lambda expressions to sort of justify currying, okay? You don't need to. If you understand it, you don't need to, but that's a good way to explain currying, okay? The other is more interesting and important, okay? Sometimes you want to write a function, but it's used only one place, okay? Only once, reference only once, and it seems very odd to just say def. In Python you do that, def, there's that. And Python you can write lambda expressions as well, by the way. So more recently Pythonisters would use lambda expressions in those situations. So functions which are written only once, I mean called only once, okay, and especially if they're small and compact, you use lambda expressions. So here's an example, odds. So what does this function do? Oh, actually we are using a feature which we have not learned, okay, but that's okay. In case you already know about map and reduce, okay, we are going to learn this in chapter 5, I think so, or 6, chapter 6, okay. But anyway, this is a prelude to chapter 6, okay. Map is a function which takes two inputs, a function and a list, okay. Actually it's more general than that, but let's discuss just lists, okay. Mapping on lists. Map takes a function and a list, and it applies that function to every element in that list and returns a list of the result you get, okay. So that's what map is, okay. We'll actually see here what's going on, okay. In this example, you might appreciate map, okay. So odds n, okay. What this does is that given, I guess, yeah, n is a number, integer, okay, a positive integer, let's say 10 or something like that, okay. And odds gets you all the odd numbers starting at 0 and ending at this n, okay. So it extracts the odd numbers from a list, okay. And f here is a function which you can see down here. We say f where, oh, is that what it does? No, odds n does not, odds n, what it does is that it gets you the first n odd numbers, okay, first n. It's not given a list as input, it's just given a number, okay. So odds is a function, okay. I didn't even realize what it was doing, but odds is a function which takes a number, positive number, and it generates a list of all the odd, I mean not all, it generates the first n odd numbers, okay. So if n was 5, it'll generate 1, 3, 5, 7, 9, okay. That's what it does, okay. And the way it does is that it generates a number 0 to n minus 1, not generates, it generates a list 0 to n minus 1, okay. And it applies the odd function, actually it applies a function to each item, okay. And that function which is applied is f of x equals 2x plus 1, okay. So that's what this is, f of x equals 2x plus 1. That looks like a math equation, but that's a full-fledged function which has a name, f here, and then x is the input to that function, and 2x plus 1, or x times 2 plus 1, okay. So if you do 2x plus 1 on each one of these items, you would get the first n odd numbers, right? So that's the example here. So here's a complete definition, and we're using the where clause, which we have learned before, okay. So where clause can be used to define a name, or in this case a function, and use that function in defining this function here. And so that's what's happening here. Now this is a little bit awkward in the sense that we are defining a function f of x and then using it here, but this function is used only once here, 2x plus 1. So it looks like it's quite verbose, okay. So this is a good place where we could use a lambda expression, okay. So we can get rid of this where f of these two lines, okay, and then replace this f by the actual function, which is the 2x plus 1, and that function can be written as lambda x arrow 2x plus 1, okay. That's how you write this f of x equals 2x plus 1 without giving it a name f, okay. So the odds function now becomes odds n equals map of this function, which is an unnamed function, on this list 0 to n minus 1, and then you get the first n odd numbers, okay. We can run this if you're not very convinced. Let's run this, okay. Oh, not that, but the next one. There you go. You got 1, 3, 5, 7, 9. Now if I change this 5 to 10, I'll get the first 10 odd numbers, okay. There you go, 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, okay. All right, so that talks about lambda expressions. Lambda expressions are quite useful even in Haskell, even though Haskell everything is lambda expression. These are called explicit lambda expressions. Okay, we are almost done here. There's the last small section here, tiny bit here, I think so. Yeah, that's a very tiny section here. This is this section is titled operator section. Okay, now this idea is useful only for operators. Okay, operators are those functions which you typically write as infix. Okay, now technically every function is an operator, or every operator is a function, so you should not be able to distinguish operators from functions from their content. Okay, but operators, I mean, the operators such as plus, minus, the ones which are used infix, okay, infix, which are written infix, those are referred to as operators. Okay, so the plus, minus, multiply, div, those things are all called operators. Okay, and there's a nice, interesting concept where you can actually use the currying or the partial applications on these operators, okay, also, and get some interesting syntax for partially applied functions. Okay, so you get some interesting, these are called operator sections. Okay, so that's the name given to that. Okay, so let's read this. An operator written between its two arguments can be converted into a curried function written before its arguments. Okay, yeah, that we have talked about quite a bit using parentheses. Okay, so for example, 1 plus 2 can be written as plus within parentheses and then 1 and 2. Okay, so this plus, which is written infix here, is exactly the same as the prefix operator within parentheses. Okay, so if I run this cell, you'll see the 3 in both the cases. Okay, this convention allows one of the arguments to be included in the parentheses. Okay, so let's see how we do this. Okay, so when you do 1 plus 2 and try to use this in the prefix, okay, in the prefix you'll say in parentheses plus, right, and then 1 and 2. Now with this and the operator section, idea is that you can take one of these inputs and put it inside the parentheses. Okay, so like this. Okay, so you can take the 1 and put it inside the parentheses before the 1 plus. So you can actually have a parenthesis 1 plus operator. Okay, and then provide it the second input, the 2. Okay, or you can provide the second input and say plus 2 and then provide the first input here. Okay, so this seems silly or strange maybe, okay, but this is an interesting one, and actually it's quite useful in many situations. Okay, so what we have done here is that we have taken the plus operator, and in particular there's no difference between plus in infix and plus in prefix, it's the same. Okay, but let's focus on the prefix idea here. Okay, suppose you have an operator which is used prefix. Okay, and in that typically we are talking about the binary operators usually. Okay, we're not talking about the unary. Okay, the binary, let's say that we are talking about a binary, okay, which takes 2 inputs. So the plus takes 2 inputs, and in this one it's written in infix, but here it's written prefix. Okay, now you have the option in an operator section of taking one of these 2 inputs and bringing it inside the parentheses. Okay, so if you do bring the 1 inside the parentheses, it has to be before the plus. Okay, why? Because it's the first one. Okay, and if you want to bring 2 inside this parenthesis, it has to be after the plus because it's the second one. Okay, so that's how we do this. Okay, seems like a game we are playing, but in general, if lambda is an operator, okay, then lambda parenthesis within parenthesis, lambda itself is the infix form of that. It's called a section. Okay, it's called the full section. Okay, but you can take the x and the y which are sitting before and after the lambda and place it before the lambda inside the parenthesis, or after the y after the lambda, and these 3 things become the sections. Okay, now the last question we have to answer is, why are sections useful? Okay, you can see that the 1 plus section using the plus operator is the same as a successor. Okay, which is basically the increment operator, right? And 1 by is the reciprocator operator, times 2 is the doubling operator, the slash 2 is the halving operator. Okay, so and these are probably true in even in the C++, C languages, or Java too, right? In the plus plus, for example, the plus plus is not an operator, but it's an assignment statement, increment, right? That looks like the 1 plus, right? So this reminds me of the plus plus operator, but it's not that. Okay, but anyway, these sections which are generated out of these binary operators, okay, there are 3 types of sections you can make. Okay, the full section, the partially applied sections with the x and the y in the right places. Those are useful because they can play the role of certain operations which are commonly done in our programming. Okay, so here 1 plus of 5 would be 6. 1 divided by, which is the reciprocator operator of 2, will be half. Okay, times 2 of 4 will be the doubling of 4, which is 8. Div 2 of 4 would be 2. Okay, so remember the div 2, the 4 would come to the left of it, so 4 divided by 2 would be 2. And we got 2.0 because div, the slash, it's not the div but it's the slash. That's the fractional division. Okay, anyway, we stop here. That's the end of chapter, is that 4? Yeah, chapter 4. Okay, we did learn how to build new functions, and we learned some pattern matches. These are important patterns, tuple patterns and list patterns. We guarded and conditionals are related to each other, and tuples and list patterns are important, and lambda expressions and also operator sections. Okay, so these are all very useful tools or useful ideas in writing some succinct Haskell programs down the road. Okay, all right, so I'm going to stop the video here. Let's see, how do I do this? And see you in the next video.